Hi and welcome everyone. In this video, I want to go over the determinants and then especially how to find the determinant of a matrix and some details. First of all, a determinant is denoted as determinant of A. That's the determinant of a matrix A. Or you can just see those two lines like absolute value. When you see that, that means you have to find the determinant of that matrix. And again, be careful. These are not brackets. These are just two straight line. And you can only find the determinant when the matrix is an n by n matrix. It's square matrix. So let's start. If we are dealing with a one by one matrix, that means only one entry. The determinant of that matrix is just that entry. And the determinant is a scalar, so it's a real number. For a 2 by 2 matrix, the determinant of a 2 by 2 matrix is just A times D minus B times C. So that's pretty straightforward. It's a formula. You can use that and find the determinant. Now, if the matrix is not 1 by 1 or 2 by 2, which will work, but then let's go ahead and see how we can find the determinant of a 3 by 3 matrix or a 4 by 4 matrix and the general formula for the determinant. So before we start that, there's some definitions. Just know what minor is. A minor is a matrix, and that's an n by n matrix. That means it's a square matrix. And the way you write it, it's Mij. So M or M sub Ij, defined as a determinant of a matrix and obtains by removing the ith row and the jth column of the matrix A. So, and I just want you to know also the minor is a determinant of a matrix that the size is n minus 1 by n minus 1. So for example, let's see for this matrix, if I want to find determinant, which we're going to get there, but let's see what the minors are. The minors, the minor M11, that means the minor of this entry is the determinant of the matrix if we hide the row and the column. That means the first row, the first column and the first row, and we see we're left with this matrix. So that's the minor M11. M12 is right here. So if we go ahead and hide that row, so the first row and the second column, you're left with this matrix, and the minor is the determinant of that matrix. For 1, 3, which is that, if I hide that, and that, you're left with this matrix. And the minor of 1, 3 is just the determinant of that matrix, the one that I just did. So this one, 3, negative 1, 0, negative 3, and I wrote it here. I did not calculate those yet, but just understand. If I say M22, M22 is this position, so you can just hide them, and you're going to be left with this number. So that's why we said if this is a 3 by 3 matrix, then those determinants are just the determinants of 2 by 2 matrices. That's why here it says n minus 1, n minus 1. Next definition is cofactor. So cofactor, the way you write it is Cij. Again, this is the row and j is the column as always, and is defined as Cij is negative 1 to the power of I plus j times the minor of Ij. So now, why do we do this? Because when we want to find the determinant, the sign is very important, and this defines the sign that you're going to have. So these numbers, if that I plus j is odd, then you're going to be left with -1. If it's even, then it's going to be +1. And we will see that in some examples. Now, if you have an A by N matrix, the formula for the determinant is given by the sum as j goes from 1 to n. That's the size of the matrix. A1j and A1j and A1C1j. Now, I put 1 in red because this does not change. This is just when you want to expand the determinant along the first row. So this is the first row, and the red numbers, they don't change. And of course, you take that entry and then you multiply it by the cofactor of that entry. And once you add all of them, then that's going to give you the determinant. Let's look at this example. I did calculate that here for you. So if I want to find the determinant of this matrix, so I must say A is that. So it's a better idea to put the determinant of A is that. So let's see, it's A11. I'm just using this formula. So it's A11, which is 0 times C11. So it's 0 times -1 to the power of 1 plus 1, as it says here, times M11, and we learned M11 is the determinant of this matrix. Then it's plus 2, which is A12, and times -1 to the power of 1 plus 2, again, because it's A12, and the minor of M12. The minor of M12, we know it's that matrix. So that's why -1 to the power of 3 becomes a negative number here. So it's -2 times the determinant of that matrix. And finally, plus 1, which is that entry, times M13. And M13 we said is the determinant of that matrix, and I wrote it here for you. -1 to the power of 1 plus 3 is 4. It's an even number, so it will be positive. So if you calculate all these determinants are pretty easy to calculate. These are 2 by 2 matrices. You just do that times that, -1 times 0 for the first one, and minus 0 times -1, and so on. And if you calculate all this, the answer should be -3. Now, when you have a 3 by 3 matrix, there's a shortcut to find the determinant. So the first thing you do, you write the first 2 columns next to your determinants, which are these columns. Then you can put these arrows. So I put the blue ones, and of course you have the red ones. And the way you find the determinant is you take the sum of the products of the blue arrows and minus the sum of the product of the red arrows. Let's go over this one by one. So the determinant is going to be 0 times -1 times 0, which is right here. Then it's plus 2 times 0 times 0, which is right here. Then it's plus, again, 1 times 3 times -1, which is right here. Then you put that in a bracket minus, then you go to the red arrows. So it's going to be 2 times 3 times 0, which is right here, plus 0 times -1, which is that, which is right here, and plus 1 times -1 times 0, which is right here. And if you simplify this, the answer is going to be the same, which is -3. Now, what we did for this matrix, we expanded along the first row. So that's what we did. However, if you want to find the determinant of a matrix, you can just expand it along any row or any column. And it's very smart if you expand it along a row and a column that has more zeros, because then you're going to get, it's going to get simpler, and then and you multiply 0, you get 0. So let's see how this works. There's a theorem that's the determinant basic theorem, and that's the Laplace's theorem. It says you can find the determinant by expanding along any row or columns. So if you have a matrix, if you want to find the determinant of that matrix, you can put, that's going to be the sum Aij. This is any row. Or I put the ith row expansion. We saw the example for the first row. So here in this case, j changes. The red one is always the same, and j goes from 1 to n, which is the size of the matrix. Here for jth column expansion, the determinant of A, here I changes, and j I wrote it in red just to show it stays the same, and I goes from 1 to n, which is again the size of the matrix. If it's, then it's a square matrix, n by n matrix. Next, if A is an n by n matrix, it's a lower triangular matrix. What's the meaning of a lower triangular matrix? Lower triangular matrix, that means you have numbers here, including the diagonal, and the top triangle, the entries of the top triangles are all zeros. An upper triangular matrix is exactly like this, but the other way around. So you're going to have numbers in the upper triangle and zeros in the lower triangle, but the diagonal is always included. Let's just know when you talk about a diagonal matrix is when we have numbers in the diagonal. See if we can show that fast. You have numbers here, and the upper and the lower triangles are zero. That's a diagonal matrix, just like the identity matrix. But if it's a diagonal matrix, you don't have necessarily all ones. You can have different numbers. Now, what it says, I just took the example of a lower triangular matrix. It works the same way for upper triangular matrix and a diagonal matrix. The determinant is going to be A11 times A22 times ... A and n. I just want you to note this means product. So basically you take all the entries in the diagonal and you multiply them, and that's going to give you the determinant of that matrix. So a fast way of finding the determinant. There is a proof for that, and induction is the best way of proving. So let's go over this proof. For induction, in my last video, I said, so what you need to do, there are 3 steps. Step number 1, you show that it's true for n equals to 1 or 2. In this case, most of the time when you deal with matrices, you take n equals to 2. So if I have a 2 by 2 lower triangular matrix, that means A11 and this number is 0, and A21 and A22. If I write the formula for this determinant, is A11 times A22 minus 0 times A21. 0 times A21 is just 0. So we are just left with A11 times A22 and BC, which is the product of the entries in the diagonal. So that works. Step number 2, suppose it's true for n equals to k minus 1. So what do I mean by that? I mean, B is a matrix n minus 1 by n minus 1. So that's an n minus 1 by n minus 1 matrix, and it's a lower triangular matrix. So, and we suppose that the determinant of B is just going to be the product of I equals to 1 to k minus 1. So, and can even say n minus 1. N minus 1, it doesn't matter if you said k, while n equals to k minus 1, we can just put k minus 1. So k minus 1, and these are the diagonals, the entries in the diagonals. Basically, you take the entries in the diagonal and you multiply them and you get the determinant, and we assume or suppose this is true. Now, step number 3, we want to show that it's true for n equals to k by this supposition. So this is the induction supposition. So let's see how it works. So I said, let D be a k by k matrix, a lower triangular, of course, always. And we want to show that the determinant of k is going to be I equals to 1 to k, and dii, again, this is the product of all the entries. We want to see if that's true. So now I wrote D in compact form. It's a k by k matrix. And of course, if we write it, we have zeros everywhere here in the upper triangle, and we have the lower triangle with the entries. Let's expand along the first row just like we did. So the determinant of D is going to be D11 times the cofactor 1 C11. So it's going to be that times the cofactor, which is negative 1 to the power of 1 plus 1, and that determinant. So we have that. If you go to the second one is going to be 0 times C12. But again, that's going to be 0 and so on. These numbers are 0 until 0 times C1k. So here, all these are 0. So what we get is D11 negative 1 to the power of 1 plus 1 times N11. So it's going to be one more time, D11 times negative 1 to the power of 1 plus 1 and that determinant. And that's also a lower triangular matrix. If I do take this one, these are all zeros. Now let's say M11 is the determinant of a k minus 1 by k minus 1 matrix. We did lower triangular matrix. I wrote it for you here. And basically M11 is exactly like a matrix here, B, the matrix B. So now if I continue this formula, so we start M11 is going to be that I starts from 2k, and dii. So I wrote that. That's M11. The determinant of this is going to be D11 times that. So which is here. Now we know this is exactly like B, so I can write that as the determinant of these guys are D11, and then, but we said that this is a by 2. We know that this is exactly like B. Let me go back to that, and then we write D11 times that. Now it starts from 2. It starts from I equals to 2 because it's that, those numbers. However, we have D11 in the front. The way I can write that, I can say the determinant, I can take that inside the product, and instead of starting from 2, we can start from n. So then we can write that the general formula. We can just say the determinant of D equals to I equals to 1 to n, because it's an n by n matrix dii. Again, if you put k here and you said k by k, this is the general one. If it's n by n, then that's going to be n. If it's k by k, then it's going to be k. So that's the very last formula, and you can put QED here. Now, one thing I want you to note, if we have an n by n matrix, of course, the determinant of A is exactly the same as the determinant of its transpose. And I put here note the proof, so please do some research to see if you can find this proof. Next, we can stop here, but next we're going to see the effects of elementary row operations on determinant of a matrix, and that will be on the next video. Thank you for watching, and I'll see you in the next video. Have a good one, everyone.